Okay, welcome to Lecture 8. What I'm going to do today is finish off what we were doing on linear systems. So I'm going to give you the final example, and then I'm basically going to go and classify all types of linear systems you can get to 2 dimensions. Because effectively what you can do using the determinant and the trace, which is the 2 main numbers that characterize the characteristic polynomial as well as the matrix the 2-dimensional matrix, is then you can actually classify all the possible solutions or types of solutions you get in 2 dimensions. And that's going to be very useful, or a useful guide, as we go on and look at more nonlinear stuff. And then I'm going to start with the nonlinear cases today. And in fact, I'm going to start with the aspect where you basically reduce them to a series of 1-dimensional problems that you then go and solve. Okay, so let's once again consider a system of linear ODEs. Once again, it looks like that. And once again, you write it in the form of a matrix times the vector. And you do the normal analysis. It's very difficult just from the matrix to know what you've got until you've actually done the analysis. And so here we get that the determinant is actually positive, right? So 2 small numbers with a minus, adding 2, and it's 17/16. So we know our 2 eigenvalues have the same sign. We also know that the trace is equals to a half. So both the eigenvalues are positive, and what you can immediately tell from that is that you have an unstable fixed point. Okay, you don't yet know whether unstable fixed point is a node or something else, and so the next thing you have to do is compute this combination. Okay, so tau squared minus 4 delta, which is the thing that comes underneath the square root, and you find that it is negative, therefore you have complex eigenvalues, therefore the thing is going to spin around the axis. Okay. And as a result, we call it an unstable spiral. And so it's basically the solution we derived in the last lecture. But what I'm just going to do now is work out the eigenvalues in full before I give you the solution. So the eigenvalues in full is simply you write out your characteristic polynomial with minus the trace and the determinant, and you solve it, and you find that the eigenvalues are a quarter plus I and its complex conjugate, and the eigenvectors are I minus 1, 1, and its complex conjugate minus I. So in the previous example, I actually worked it out from first principles, the general answer. You can do that as well, or you can use the formula I actually derived 2 lectures ago, and you can write it down. And the main reason for me giving you this example is, if you look at this formula, right, there are things that depend on time, and there are constants. Okay, and the mistakes I've seen in the past is that you must remember the things independent of time is fine. This x0 is actually the initial point where you start. Okay, so this is basically the xy coordinates of your initial point. This sine t depends on time, and then the second constant, okay, and I've already filled in the omega and tau, so omega and tau go in here. The second constant is actually a matrix, so it's A minus 1 over 4 times I times your initial condition. So if you actually write this out in full, here we go. So it's x0, y0 times cos of t, e to the 4t I've taken out in front, and then it is A minus a quarter I. So it will basically be minus a half, minus 2, 1, and 1 multiplied by y0. Sorry, A minus a quarter I. That will be a half, multiplied by y0. And so you're going to have this combination of constants coming in times sine t. Okay, so just be careful. This last part that's in front of sine t, we actually have to multiply out the matrix with x0 is what we have caught people in the past. Okay, so that's your solution now, and we now want to plot it. In fact, we preferably want a way of plotting it without actually knowing what the solution is, because that'll just make it easier. And so what we do is, firstly, we put our axes down. We once again plot the null lines, and this is the thing you're going to, this habit of plotting all the null lines is one that should stick with you all the way up through nonlinear systems. So you basically have x dot is equals to 0, which means that you have y is equals to minus 3 over 8x, and you have then put on the arrows. You know that x dot is equals to 0, so the arrows either point up here on the right or down on the left. And then here you have y dot equals to 0, so the arrows either point left or right on that line, and you see y dot is equals to 0 when y is equals to minus 4 over 5. Okay, so there you go. They point right and they point left, and so you can immediately get a feel that something is going to come and cross that line, it's going to make a turn, and then it's going to go up. Okay, so that's what these two lines tell you. The next place, because we don't have real eigenvalues, we're not going to be able to plot. We don't have an obvious extra line to plot. And so what I do then is I plot the arrows on the x and the y axes. Okay, so on the x-axis, it's very easy. When y is equals to 0, you see that x dot is negative and y dot is positive if x is positive. So they point inward like that. And when x is negative and y is equals to 0, you have that x dot is positive and y is negative. Okay, so they point down. Similarly, you can do it on the y-axis, and you once again set x equals to 0 over here, and then you have that when y is negative, x dot is positive, and y dot is negative, so it's pointing down into this fourth quadrant, and when y is positive, it's pointing up into the second quadrant. And so you can now see that there's a very definite feeling that it's making a little loop over there. It gets the axes, it crosses the axes, it keeps going till it hits the next axis, it crosses that, then it gets flat over there, it makes a loop, comes down, and then crosses its axes and goes on like that. And we know that because tau is positive, right, the actual amplitude of your ellipse is going to increase in time. So it's basically going to start here, go around, and spiral out. Okay. And that's exactly what we see. Okay, so you can actually draw this thing without having had the general solution. Okay, which will be useful later on, where I'll actually expect you to draw these things without having the general solution, but know how to make this general solution, especially if you're going to get it directly from the solution I derived, where you're using the matrix and the eigenvalue and frequency multiplied by x0. Okay, so there we go. So that's the last example I'm going to do. What I am going to do next is give you a general summary of what is possible for all linear systems in 2 dimensions. And this is an important plot. I keep it whenever I do dynamical systems because it just makes it so easy for me to try and actually get a picture in my head of what's going on. So the first thing is, we've had the case where we've characterized our solutions. When we do all these examples, the first thing we compute is the determinant and the trace of the solutions. And then giving the determinant and the trace, we can sort of give an idea of whether it's stable, unstable, and whether it is a spiral, a node, or something else, or a center. And so I just want to put all of that on one plot. So we have that our eigenvalues are basically dependent on the determinant and the trace in the following way. So here you have the trace coming in that influences whether it's stable or unstable. Here you have this factor that comes into the square root that makes the difference between complex and real eigenvalues. And what I'm going to do now is I'm going to plot this line of tau squared equals to 4 delta, okay, just to give you the transition between real and imaginary eigenvalues. Okay, so there we have it. And so on this plot now, I'm going to put all the possible phase diagrams we have. So once again, the determinant is vertical, the trace is horizontal, and this thing is the difference between real, or the parabola is the difference between real and imaginary eigenvalues. Okay, so the first thing is, if delta is negative, remember, the two eigenvalues have different signs, and you have the case with the saddle. You always have the arrows coming in along the eigenvalue that shrinks or is negative, and then they get thrown out along the eigenvalue that is positive or the unstable direction. Okay, so this direction where it comes in is called the stable manifold. The one where it goes out is called the unstable manifold. And so all the way, as the moment delta is negative, you can immediately say it's a saddle. The next thing is, suppose we're sitting over here where we have the delta is positive, the trace is negative, or the trace is negative, so it's stable, and delta is less than a quarter tau squared. Then what we have is a stable node. And so this whole region over here is always characterized by a stable node. Similarly, if we go to this side now, we once again have real eigenvalues sitting over here. We have tau is positive, so it's unstable, and so we have an unstable node, which is basically the stable node with the arrows reversed. Okay, if we have an imaginary eigenvalue, in other words, we're above this curve, but we have a negative trace, then we have a stable spiral, which is the example we did in the previous slide. If we have a positive trace, however, we have an unstable spiral where it spirals out to infinity. Okay, so that's basically done all the cases except for the special cases on the line. So if we have the trace exactly 0, so we're on this line, we have that, we have a center. In other words, it's neither stable or unstable. And a center is an interesting one, right? It's a kind of solution we could never get when we had just one dimension, right? This one is also one we could never get if we just had one dimension. So these two require two dimensions to exist. So that's the center. If we are on this line where tau is negative, and we have the two eigenvalues basically transitioning between real and imaginary, or rather the two eigenvalues exactly the same, then we have what we call that stable degenerate node. That's when we had to do the hard work of constructing the extra vector that wasn't an eigenvector to be able to write down the solution. And we had a solution that was exponential and then had a polynomial part in T. So that's the stable degenerate mode. Over here on the other side, if tau is positive and we're sitting along this blue line, we have an unstable degenerate mode. Okay, so very, very close to a stable node. It's just that we no longer have two eigenvalues that are distinct. Over here are some cases that we have not captured. In other words, when the determinant is 0, that means that one of the eigenvalues are 0. And that means your solution basically looks like a line of fixed points. It's because if your eigenvalue is 0, all the points along that eigendirection is a fixed point. So this is what we have here, basically a line of stable fixed points. Over here, we have a line of unstable fixed points. You basically have a line where the eigenvalue is 0, but just immediately off of it, the other eigenvalue is positive, and it will push it away. The final example is over here, where both the eigenvalues are 0. Okay, and if both the eigenvalues are 0, you basically have x dot y dot is equals to 0. Therefore, xy are just a constant, and therefore we have what they call uniform motion. So it's just a trivial case. Okay, So this basically summarizes all the possibility in two-dimensional linear systems, and there's a complete analytic solution. It can be completely analyzed. All the possible phase diagrams you get are these. And so what we're going to do now is build up more complicated phase diagrams using this knowledge. So just to comment to this week's problems, it doesn't have to be handed in. You just have to work through the problems on your own. So please do that, because it's a very important building block for what comes next week. Okay. And come with questions in the TUT tomorrow if you have any. Okay, so let's now go on to general two-dimensional systems. And just to remind you the definitions, because this becomes more important as we go more generally, that's a general two-dimensional system. X dot equals to a function of xy, and y dot equals a function of g, where both x and y in the plane are 2. And you basically view x dot y dot as the velocity vector, which is what we've been plotting in the phase diagrams at each point, and your ordinary differential equation defines this field, the vector field in the two-dimensional xy plane. And then just the definition, our fixed points is a point that satisfies x star y star equals to 0, f of x star y star equals to 0, and g of x star y star equals to 0. And the reason I'm repeating this is that we're going to use those definitions at each fixed point. So the basic approach is we're going to get the system with any f and g. We're going to look for where their fixed points are, and then about those fixed points, we're going to do a Taylor series expansion, linearize it, do the phase diagram around that fixed point, and then just draw in the phase diagrams in between. And it's always possible to do that, and that is the way we then structure our linear system, or sort of our general systems phase plane from a whole bunch of linear systems. So let's just define mathematically what the linear system is. A linear system, linearized system, is always about a specific fixed point, and we use that to classify the fixed points. Okay, we also use it to build the phase portraits, and the way we go about it is we're now focusing on the system near a particular fixed point. We're going to let u be the deviation of x from that fixed point, and v be the deviation of y from that fixed point. And then what we're going to do is, since x star and y star are constants, in other words, it's a particular fixed point we are working with, we can say that u dot is equals to x dot, and v dot is equals to y dot. And then we're going to basically write down our expression for u dot and v dot, which we derive from the full general nonlinear system, and we're going to do it by linearizing that system about the fixed point. So what we do is we have that u dot is equals to f of x star plus u and y star plus v, and we're going to Taylor expand this expression about the fixed point over there. And the way we do it is simply a two-dimensional Taylor expansion is simply the function at the fixed point, which by definition is 0 actually, plus the derivative of the function with respect to x evaluated at the fixed point times u, plus v times the derivative of the function with respect to y evaluated at the fixed point, plus terms of u squared and v squared. Okay, and as I said, f at the fixed point vanishes, so we're left with this expression. And so the linearized system is basically the system that argues that these guys, you're not very far from the fixed point at all, so these guys are small, and the main part of the system is affected by this. And so instead of solving the full system, we're going to simply solve the system over here. And you must know that f of this derivative evaluated at the fixed point and the derivative of f with respect to y evaluated at the fixed point are constants. Okay, you can do exactly the same thing for v dot, except that you've now replaced f with g. Okay, so we have these two expressions, and the result is that we actually can get this linearized system for U and V. So the partial derivatives of f and g are evaluated at the fixed point. In other words, they're numbers. Okay, so we basically, the technique when you solve these systems is, one, you get the system, you find all its fixed points, you then work out these derivatives, and you evaluate them at the fixed points, and you look at every single fixed point, and you try and classify what it is. Okay, and this combination of derivatives over here of these functions is something we call a Jacobian matrix. So if you look at the system, you can once again write it in the linear form by simply putting all these df dx, df dy, dg dx, dg dy into a matrix and evaluating it at x star, y star. Okay, and this matrix is what we call the Jacobian matrix. It's a matrix that appears whenever you change coordinate systems. Okay. When you have work out volumes in polar coordinates, volume integrals in polar coordinates, you're always going to have an extra component that comes in like r times d theta dr, and that r is also the determinant of this Jacobian matrix. So it appears not only in this context where we've derived it, but it appears in many other places. It's a very natural thing to linearize a problem at a specific point. Okay, so just for now, it's a definition. The Jacobian matrix is defined like that. It's basically the first partial derivatives evaluated at a specific point. And using A, you can simply write the expansion in that way. So we now have a genuine linear system which obeys all the properties we've had in the previous slide and which we can basically use to evaluate what the problem looks like at the fixed point. Okay. And so we're going to basically, near the fixed point, these things are very, very small, and we can neglect them, and this basically gives you this final linearized system, which we now solve. Okay. So whenever I get a fully general two-dimensional system, the first thing I do is, one, compute all the fixed points. The next thing I do is work out the Jacobian matrix, and then I simply use that to construct a linear system, which I then solve. And so let's look at one example. Okay, so this is a classic example. It was one of the first model examples. It's called a Lotka-Volterra Model. It's basically how two populations interact. So there have been a number of cases where people have reintroduced wildlife. The one classic one, there was an island where they put deer on it. And the deer, eventually there was a population explosion and they were eating too many things, too much of the grass. They were completely deforesting the island. And so they introduced wolves. And they wanted to know how many wolves they would introduce and what would happen, and whether they would, how they should do it, so that the wolves don't, because now the moment you introduce wolves, they're like, ooh, lots of food. So then they're going to eat the deer very rapidly. If you introduce too many, they thought, then you would just decimate the population. And they wanted a model to know what it would be like. And this is one of the models that they made up. So what it is, it's basically a model for two species for the same but limited supply of food. You basically have a population, say, of rabbits, and that population you denote by X, which is always positive. You have a population of sheep. So it's not. So this is not the case where the one population eats the other one. This is just they have the same food that they want to eat. So you have a population of sheep that's also positive Y. And independently, if you were to just introduce the rabbits or introduce the sheep, the rabbits would breed like crazy, or the sheep would breed like crazy, and you would have logistic growth. So they would breed rapidly, have that very rapid initial increase, and then they would saturate at the saturation value. Okay. And the growth rate for sheep is less than for rabbits, because sheep can multiply less. Sheep's gestation period is longer, so they multiply slower than what rabbits do, which can breed. They basically breed right rabbits. Now, the next term is that competition, if somebody has to fight for food, they're less likely to breed at the same rate. So the model goes and it says competition is going to reduce the growth rate of both the rabbits and the sheep, but in different ways. Okay, the reason they say it's different ways is that it's easier for sheep to bully rabbits than the other way around. So the rabbits are going to be affected more, and the sheep are going to than the sheep because they're smaller, so they're easy to bully. And so the model that they made up was basically as follows. Okay, so here is the thing for the rabbits. So you have that logistic growth. Remember, the logistic growth is always quadratic in the population. 3 is roughly the growth rate. Okay, and then here it saturates over here. And then here is the term that this logistic growth is now going to be decreased by minus 2xy. So this proportional to the product of the two populations. So the more sheep there are, the bigger this term is going to be. Okay, and so just another way, this way of writing it makes the model clear. This way of writing it makes the mathematics clear. Here we go. This is the sheep's model. Here you have the fact that their growth rate is less. In other words, they produce less quickly. But this minus xy is less than the one above because they're affected less by the competition. And once again, you can also factor it out and write it in this way. Okay, so there is a model. This thing is definitely nonlinear. It's nonlinear in a cross term. In other words, there's an xy term. And it's also nonlinear in terms of x over here. Right? There's an x squared term over there and a y squared term over there. And so our approach to solving this problem is, first of all, find all the fixed points. And to find the fixed points, you're going to have x dot equals to 0 and y dot equals to 0. And this is where it gets tricky, right? You have to find all the fixed points. So the way you go about this is you say, what do I need to have x dot equals to 0? So here you can see you either need x equals to 0 or you need y is equals to 3 minus x over 2. So there are two possibilities. So you basically pick one and you see what that implies over here. So if x is equals to 0, then you're going to have two possibilities. You can either say y is equals to 0, or you can say y is equals to 2. And you must write both of them down because both of them are valid fixed points. Okay, so if x is equals to 0, y is equals to 0, or y is equals to 2. If y is equals to 3 minus x over 2, if 3 minus x over 2, then you have to put that into this expression and find out what that means. Okay, so if y is equals to 3 minus x over 2, it means that for y dot be 0, you either have to have y equals to 0 and x is equals to 3. In other words, where that thing is satisfied and this first bracket is satisfied, or you have to have where you simultaneously solve this equation and that equation, and that happens when you have 1, 1. Okay, so it's very important when you do these problems to find all the fixed points. Okay, and the way you do that is you go to the first equation, find all the conditions for fixed points over there, and then look at every single one and see what it implies for the next equation. Okay, so the next step we're going to do is we're going to look at the null clines. Okay, and we know that, so the null clines, once again, or remember when x dot is equals to 0 is an example of a null cline, and there the null cline is basically here x is equals to 0 and y is equals to 3 minus x over 2. Okay, and it's very important to know that the fixed points will always occur on null clines. So this is another check that you put in. Compute all your fixed points. When you start doing the plot, you should plot all your null clines because there it's easy to draw the arrows, and definitely make sure that all your fixed points are actually on the null clines, otherwise you made a mistake somewhere. Okay, the second null client is when this lower one, y dot, is equals to 0. So that's y equals to 0, and y is equal to 2 minus x. Okay, so we've done the null clients. The next point is to study the linearized equations at all the fixed points. And to study the linearized equations, you've got to compute that Jacobian matrix, which is the derivative of f with respect to f with respect to y, g with respect to x, g with respect to y. So over here, for this problem, f is that whole expression and g is this whole expression. So we can actually go about and compute it. So if we take this thing's derivative with respect to x, we get 3. Here is a minus x squared, so it's 2x minus 2y. If we take this top one's expression with respect to y, we basically get minus 2x over there. If we get g's expression with respect to x, we simply get minus y, and with respect to y, we get that expression. Okay, so we can compute our Jacobian matrix simply by taking derivatives of the differential equation. And what we do next is at every single fixed point that we have, we now work out what the linearized system is going to be like. So at 0, 0, we evaluate A at 0, 0. And what we do then is we get this, so it's 3, 0, 0, 2. We then have to go work out the determinant and the trace, work out the eigenvalues, and then work out the eigenvectors for this case. And so we do it, and this is the reason why you have to get very fit with a linearized system for this problem set, because you can get problems like this next. So just one trick. If you have a diagonal matrix where you in 2 dimensions only, and one of the eigenvector or one of these off-diagonal elements is 0, then automatically your eigenvalues are simply the values on the diameter. Okay, so that's just a quick trick if you're running out of time for some reason. So we know that the eigenvalues are 3 and 2, and it's an unstable node, and the associated eigenvectors are simply 1, 0 if the eigenvalue is 3, and if it's 2, it is 0, 1. Okay, and the other thing you can do is identify the smallest eigenvalue if it's a node, because that's the slow direction, and that's because it's unstable, that's where your solution is going to leave along, right? Remember I said there was a fast and a slow direction, and the slow direction is where the solution departs from the fixed point. Okay, 0, 2, you once again go, you substitute 0, 2 in here, you get the numbers that your matrix at 0, 2 is minus 1, minus 2, 0, minus 2. You once again note that there's a 0 element, so your eigenvalues are minus 1 and minus 2. Okay, so it's a stable node because your eigenvalues are real and the trace is negative. And here's your first eigenvalue. Okay, you can work out the eigenvector. It's the slow direction because it's the smallest absolute eigenvalue. Your other one is the fast direction. You work out the eigenvector associated with it. Then you go on to the next fixed point. So it's 3, 0. You substitute that in, you get what the matrix is. Once again, you can see the eigenvalues are minus 3, minus 1. So it's another stable node. You work out the eigendirections for each one. So for the minus 1, the eigendirection is 3, minus 1. It's slow. For the other one, it's the eigendirection is minus 3. And, sorry, the eigenvalue is minus 3 and the eigendirection is this. And we finally get to the final fixed point. We do the same thing. We substitute the values into the matrix. We get that the matrix's constants are minus 1, minus 2, minus 1, minus 1. This is harder than the previous ones because you can't just write down the eigenvalues. So you work out the determinant, which is minus 1. So you know it's a saddle, right? Because the 2 eigenvalues are different. You work out the trace, which is minus 2, but it still remains a saddle. And so you simply go work out the characteristic equation and find that the two eigenvalues are this. They are real eigenvalues, they're just not very pretty. And you work out the eigendirections, and you know that it approaches the eigendirection along the negative eigenvalue, so that's C minus. Okay, so that's all the algebraic work you need to do for a nonlinear model. Where it becomes interesting is where we actually start working out the phase diagram. So what I'm going to do now is I'm going to take all the stuff we've learned from the linearized analytic work about the various fixed points, and I'm going to start plotting the model. And this is where it becomes important to be able to fill in all the details. You need to do this hard work, but you also need to be able to put it together on the bigger plot. Okay, so let's plot the model. Okay, so here are our differential equations. The first thing I do is I put in all the fixed points that I have, and I've classified them, and I indicate whether they are stable, like those two, or unstable over there. In fact, remember 1, 1 was the saddle. Here at 0, 0, you had an unstable node, and then you had two stable nodes here on the axes. The next thing I do is I put in all the null clines that are computed. So remember, the null clines are when x dot, oh dear, when y dot is equals to 0, the null cline is y equals to 2 minus x. So it's this line. That's one of them. I put in the arrows on that line. Okay, so remember y dot 0, so it's either arrows left or right. Here they're right, over at the top they're left, so that's done. The next null cline is, there's not just one, the next one is when y is equals to 0. So next null cline is here along this axis. Okay, so there's a null cline that's a bit hidden over here when y is equals to 0, and you put the arrows in there as well. Okay. Now, the next null cline is when x dot is equals to 0 and y is equals to a half 3 minus 2. And so it's this line over here. And as I predicted, you can see the saddle is on two null clines. This 2 is on a null cline, and this 3 is actually on two null clines because it's on the x dot equals to 0 and the y dot equals to 0 null cline. And so what we want to do is we want to put the arrows in. And you can start seeing, so here they are down, over there they are up. Generally, arrows may change after you've crossed the fixed point. Okay, that's just another thing to look at. And so you can see over here, it looks like along this dark cyan null cline, they all go to the right, and along this lighter one, they all go in down. So sort of this is a region where the null clines are going to, or the trajectories are going to collect, and then eventually they're going to go to this fixed point over here. Okay, so we put in the arrows. The next one is that along here there's also a null cline, right? X dot is equals to 0 when x is equals to 0, and you put in arrows that point up. Okay, so we've done all the null clines now. What we're going to do is look at each fixed point individually and plot the eigenvalues, plot the eigenvectors. So remember, for the 0, 0, it was an unstable fixed point, and you had the eigendirections were simply the axis directions. Okay. For 0, 2, it's a stable fixed point. One of the eigenvalues went along the axes, and the other one, and it was the one that approached it, over there, the other one is this one that went in, and it lies between these two null clines. Okay, so once again, you can see these two null clines basically implies that all the trajectories flow across that null cline into this area and up across that second null cline into this area, and then they're going to approach the fixed point along this eigendirection. Okay, this 3, 0, 1, we once again plot the eigendirections for it. So you basically have them approaching along the axes, but the second eigendirection lies over here. Okay. And then the 1, 0, you're going to plot all the eigendirections. There's the 1 that it approaches the fixed point, so that's the stable manifold. And there's the other one, because it's a saddle, that they depart from the fixed point. So you sort of can get the feel already that from here, the trajectory is going to sort of go up, approach that fixed point, get kicked out, and then it's going to go to this fixed point over here. Okay, so now you can see that solutions are going to approach one of the two stable fixed points. In other words, they're either going to go here or they're going to go there, right? Because they're going to run away from the origin and then they're going to basically go up. They're either going to spin around and go over there, or they're going to go up over here and then approach the saddle and then go over to that one. Okay, and in biology, this is what they call the principle of competitive exclusion. It's basically one species thrives and drives the other one to extinction. And it's one of the reasons why farmers tend to keep their different types of flocks separately, because they don't both thrive at the same place. Okay, and so it's pretty much illustrated with this example. And just to be able to be very careful about which one, how you plot the regions where the solution goes to the one fixed point and how you plot the regions where the solution goes to the other fixed point, is this idea of a stable manifold. Okay, so a stable manifold is usually defined for a saddle. Okay, it's the set of all initial conditions that approach the saddle. In other words, and that's a very small set. Like all the initial conditions that approach the saddle are those that only are going to enter over there along the stable manifold. Okay, so it's a set of all initial conditions whose trajectories approach the saddle. So it's just basically a line of fixed points as t approaches infinity. Okay, and that thing is going to be the basin of attraction. Okay, it's going to be the line that sits between the solutions that go to this fixed point and the solutions that go to that fixed point. And if I have to draw it, this is what it looks like. So this line you cannot draw analytically. The only thing you know about it is that it is tangent to this eigendirection as it comes in. The other thing you know about it, in this particular example, it's got to come from somewhere, and it's going to come from this other fixed point. And the way we actually draw this line is you take a computer, you put it a little bit epsilon from the fixed point along the stable eigendirection, and you integrate backwards. So that's how I made that line. Okay, it's a very unique line because anything else is going to go either to this fixed point or it's going to go to that fixed point. But only this line is actually going to go to the saddle. It's an infinitesimally small line. Okay, and that line is the line that separates where the solutions actually are going to go to the one fixed point or to the other one. Okay, and I can do the same thing over here. I can go epsilon away from this fixed point along the eigendirection that enters it and integrate backwards, and then I'm going to get you this other line that is forever going to separate the solutions that run to this fixed point and the ones that run to that other fixed point. And it's called the separatrix between the two basins of attraction. Right, it's okay, so just the basin of attraction of an attracting fixed point x is mathematically defined as the set of all initial conditions x0 that approach a particular fixed point as t approaches infinity. So in other words, anything that you start that eventually ends up at this fixed point is in the basin of attraction of that fixed point. So in this example, it's everything below the purple line. And in this example is everything above this purple line. Okay, so that, except for actually drawing, in this example you can guess what the separatrix is, But everything else I put on this graph you can get from the linear analysis, and I expect you to do it. What you can't do easily is once you've got this, you can start drawing in what the trajectories will look like. So you can simply guess that if you go along here, it's going to hit this fixed point. If you shoot out there, it's sort of going to go up and then cross this line and hit that fixed point. Or you can go to a computer program and draw it. So that's what I'm basically going to do now. So these lines are actually the exact solutions that I've numerically integrated, and I'm going to stop once I've given you all of them. So here you have the line going to the fixed point. You have another one. If you shoot out with a slightly different trajectory that's closer to the separatrix, you're going to go up, cross the null line, and then move away from the saddle along this eigendirection, but you can never cross this other one, and you can approach that fixed point. If you're coming from a large X, large Y situation, if you're below the separatrix or the purple line, you're going to go to this lower fixed point in that way. So I've basically drawn examples of initial conditions that go to the 3-0 fixed point. If you now go over here, you can do the same thing. It's going to go up, it's going to approach the saddle, it's going to then approach the fixed point, and you can do that for all of them. Okay, so you can learn a lot about your phase diagram without even knowing how to plot the trajectories simply from the linear analysis. And this is why it's so important to get that linear analysis down pat now, because you're going to use it a lot. But it's a very, very, very powerful tool. Okay, I'm going to stop there. What I'll do next is I'll talk a little bit about the Python code that I did this with, just so that I put up on during the TUT, that I put up on the website, so that you can draw it yourselves, because it's very nice to actually be able to draw this. It's fine with me if you use MATLAB. I can tell you what the programs are, but I'll discuss this more in the TUT. Thank you very much.